app benchmark accessor. It is a distribution that was published in, I think, 2011 that shows comparison between different accessor builders. And, well, you can see it in action, so, it's a little bit unstable, and that's one of the things that I'm going to be talking about. So. It's right here. No, because it's written badly, among other things. We'll get to that.
Ich habe versehentlich auf heißes Wasser auf den Bock gedrückt. Das ist richtig heiß. Das ist der Vortrag. Da wurde sogar noch ein Stückchen gerissen. Also bei 2,25 Jahre. Und du hast aus dem Kaufgeld das Geld, das ist der Benchmark. Also im Fall hat oben ja, nochmal wieder auf funktioniert. Okay, jetzt machen wir das.
What's that? No? So. This just running as as a screensaver, so it's not very important. All right, so I should be starting. Yes. All right, so there's a lot of you today, I guess. So this was supposed to be a talk called "Benchmarking is Really Hard," and I was supposed to show you a triumph of reproducible benchmark results. Unfortunately, I'm not going to do that. I'm going to talk to you about adventures in failure to do that. My name is Peter Rabbitson. Most of you know me by ribasushi. I have been the DBX class toolchain chainsaw since 2008, and I generally complain about stuff running too slow or not well enough, and so on and so forth. And I suck at slides in general. Those slides are not very informative, but we'll get there. And I again am available on IRC these days under the link ribasushi, and of course you can reach me by email. So, why do we benchmark? In general, we often need to know if something that we are trying to write is a good idea before we wrote it. We want to have a proof of concept and kind of run it through and see if it's okay. And also in a system that we already have and it's running too slow, we want to see if we change this little thing here without writing pretty much everything else to suit this little change, if it's going to give us an improvement. And of course, we do this kind of stuff for shiny comparisons. Like, for example, we want to know that the thing we're writing is on top of the list. Well, in this case, it's a bad idea to bet it on the top of the list, but you know, even that you want to know. So, why am I talking about benchmarking, about not profiling? Because generally, when you have something that's slow, you want to profile it first and see which part is slow and so on and so forth. The premise profiling is that, first of all, it requires a complete working system. So you have something with its business requirements already fulfilled, it's already running, and it's slow, and you want to see which part is running slow, right? So you can fix it and stuff. Of course, this doesn't really work on a proof of concept because, well, you have nothing to compare to at first. And also, profilers compare, pretty much that's their definition, they compare apples and oranges. They take your entire program and they run every single piece of it once, and then they show you which one supposedly ran the slowest. And you make your decisions what's to optimize from there on. In general, I'm interested in microbenchmarking because I like optimizing very low-level stuff. I like optimizing accessors. I like optimizing run loops. I like optimizing variable assignments. I like skipping unpacking at underscore because it matters in microbenchmarks. And famously in Riga, I think it was, I'm pretty sure, Paul Johnson, who I don't know if he's here today, he had a lightning talk that basically explained that it doesn't matter. Micro benchmarks are not that big of a deal in the big, in the grand picture of a program, but it doesn't matter until it does, because if you take many small improvements and you multiply them by the many calls that normally happen in a program, like for example, how many times do you call the same accessor over and over again in your program? You can measure it, it will easily go into the tens of millions. Any small improvement automatically will give you enough winning to call Charlie Sheen, most of the time. In general, something that will shave 10% of your execution in a benchmark, normally on such a low level as an accessor or something like that, might very well speed up your program by good 30–40%. Like we're talking on the micro level. Right, so, of course when you start benchmarking, especially if you start micro benchmarking, and I guess I need to explain what micro benchmarking means. For example, you want to benchmark how quickly Perl adds 1 + 1 10 million times. This is called a micro benchmark. We basically take a very small amount of operations and we see how fast they execute. Okay, or in a more useful case, we take an accessor, which is generally a pretty simple operation. It's basically just arrow on an object and the name of the accessor, nothing else. And we want to see if different implementations of this thing actually give us better or worse results. And the challenge in this kind of benchmarks is reproducibility. And as you saw, this thing, for those of you who are in the back, sorry, but basically what it does is, this is an instance of one of the tests that ship with app benchmark accessors. And it is cut down so I can run it somewhat in real time. There are many more tests in the actual distribution. But what it does, it compares class accessor fast, moose and moose immutable object accessors to each other. And as you can see, we get sometimes something is 2% better than the other. Oh, okay, now they reordered. We have moose immutable is 4%. Oh, moose immutable is actually 11%, and so on and so forth. So we cannot really make a sane decision based on that. So why is it so hard to reproduce, and why a benchmark, when run once, shows one result and then it shows a completely different result? There are several reasons for that, and they're kind of outlined here, and we're going to go into detail. But the main points are the CPUs are way too smart these days, the hardware is cheap, another word for crappy, the operating systems do too much, and the software also, the actual library stack, starting from libc up, is pretty sophisticated at this point. So, smart CPUs. these days, in 2013, we already have, you cannot buy a processor which does not have some kind of frequency scaling built in, which is very aggressively used. So we have features like Intel Turbo Boost or AMD Turbo Core. We have aggressive thermal management. The moment the CPU decides that it's getting, it's running a little bit too warm, it will scale itself down. The moment it decides that it's running too much power on one of the buses, it will scale itself down. Cache sharing. This is horrible because these days, caches on CPUs are always less than there are cores. There are very few CPU designs that actually have a dedicated cache per core. So you not only have aggressive cache sharing, you have unavoidable cache sharing, which means that your pipelines get completely jumbled together anytime you try to execute anything concurrently. So your measurement is completely off the chart. And as I said previously, you cannot get a physical system anymore that will not have something like this turned on in various combinations, screwing up your numbers big time. Cheap hardware. What means cheap hardware? The high frequency clocks are actually extremely unstable. I ran a bunch of simulations where I tried to write the simplest C program possible and time it on CPU time instead of wall time. And I would get, on a completely quiet system with as much precautions as possible, I would get completely different results. So, even the high frequency clocks, you cannot really trust them. Operating systems. Any operating system that you run on your laptop, on your desktop, or whatever, it has to do a lot of stuff in real time, in the background, concurrently. There are all kinds of daemons. There are all kinds of things that actually deal with the virtual management of these daemons. There is all kinds of stuff that deals with, with the cache systems, with the virtual memory. Even moving your mouse actually brings your CPU momentarily, but it brings it up to about 30% of usage, especially on Linux if you don't have access to most of the hardware. Acceleration, it's really, really bad. And if you're not careful, on most of the systems these days, you run this kind of stuff. You have a Prism user client, somebody is using your JavaScript to mine Bitcoin, somebody is running Freenet without your knowledge on, and yeah. That's reality today, okay? Right, so, another problem, which we talk about smart software, and we're talking libraries, virtual machines, and so on and so forth. David Golden made a pretty good summary of this, like about 6 months ago or something. He wrote a replacement for Path class. It's called Path Tiny. It's pretty cool. Check it out. That's what it says on the tin. And he wanted to see how quick is it compared to the competition. And what he came up with is what he calls, it sucks to be called L. What he's talking about is that he took the same code, as you can see right here, absolutely the same code, okay? And he executed it, well, benchmarked it several times under names that are called A through L in the hash. Nothing else changed. The code is the same, everything is the same. And he got results like this. L came in last, and D was really, really, really fast. And so, is it hopeless? It actually is mostly hopeless, in my experience. But of course, we can mitigate some of these problems. First of all, system-wide. At first, I'll put ventilation. Why? I actually had a version of this talk last year at John McCall workshop where I risked to do a live demonstration. Instead of having boring slides and stuff, I actually wrote a little program that cycled through different ways of benchmarking stuff and showed different results and stuff like that. It ran excellent. But it was March. I came to actually here in Kiev, to Yapsi, Russia, 2 months later, and nothing worked. the entire presentation was a disaster, absolute disaster, because my laptop would go into overheating mode and it would scale itself up and down, and I not only could not show consistent results, I could not even arrive at results. It would just sit there and spin, you know, and yeah. So first of all, make sure that your machine on which you're running your benchmarks actually has adequate cooling. It matters big time. Reduce amount of background processes, what I already spoke about. It's common sense, but most of the time it evades people that listening to music as well counts as a process in the process of benchmarking. Another interesting thing is that most of the time you can lock your CPU from frequency scaling. It's not perfect, but it works well enough. And unfortunately, I do not know how to do this on most operating systems, but at least I know how to do it on Linux. On Linux, we have this thing on modern versions of Linux. We have this thing called sysfs, which gives you access to the actual governing information of the CPU. What is its allowable minimum frequency and what is its allowable maximum frequency. In fact, the scaling governor actually does not mean much in these cases, because no matter which one you select, it's still going to jump all over the place. That's just a fact of life. So a nice trick that you can actually use, and which most of my benchmarks these days actively check for, you make sure that you set your max frequency to your minimum frequency. This is most of the time sufficient to load the CPU into a state where it will where it is unlikely to overheat, and it is definitely not going to jump into a higher state, so your benchmark will run longer, but at least it's going to be somewhat consistent as far as the CPU frequency on which this benchmark is executed happens. Proper tools. Do not use benchmark PM. It is still part of core. It is still part of core, right? Yes, it is. It's still part of core. But it is a very, very bad idea. The stuff that I showed you earlier runs on benchmark PM, and it is very inconsistent. By default, it doesn't even use a high-resolution clock. And instead, use the bench written by Stefan Müller. He did an excellent job by taking the concept of timing. He didn't really go into how we actually time stuff, but once he got the timings, he went and used very sophisticated statistical analysis to figure out what exactly is the actual time which something took to run. He calculates himself how long the stuff will run. He calculates himself how many times it should pre-run, how many times it runs after that. You only ask for a specific precision, and you just let it run. You know. And it's actually pretty easy to use these days. If you have code like this, so you have the usual benchmark PM, you compare this with high-resolution wall clock, and you run everything for 1 second at least. And of course, you call your subroutines not L, because we already know it's a bad idea. And this is what a normal benchmark looks like. To run it on the dump bench, all you have to do is change benchmark to benchmark dump. And instead of giving it the negative time, you give it how many times to run it, right here, the 0, how many times to run it, or determine automatically, and the precision that you're interested in. And this is it. This will give you already a much, much, much better result than benchmark would give you. Use CPU time. Most of the benchmarks that I have seen, benchmark frameworks that I have seen, they use the wall time elapsed since it started the timing until the iteration ended. The problem with this is, again, the multitasking of the OS is you do not know how much other stuff happened in this slice of time when your program was running. Yes, you will quiet down your machine, but even then there are OS things that run that you cannot shut off no matter what you do. So that's why, specifically for dump bench, I normally do this. It's a hack, and it's a hack because it is not currently simple to pass many options to dump bench. But basically, if you have code like this, what I do before I measure, I simply replace the time highest time with clock process CPU time ID timer. So I simply substitute the time highest time function to return the CPU time instead of the wall time. And also this changes my benchmarks by a good like 20% or something like that, just by doing that. So again, good thing to have. And most importantly, just what we benchmark. Perl is slow. The language itself is extremely slow. Calling a function is has an overhead normally much bigger than the thing you micro-benchmark. Also, crappy clocks, I spoke about this. If you do more than 1,000 iterations of something per second, you cannot trust this timing anymore. You just can't, because it will be just a little bit different enough to give you a 1% deviation. So what you do is you turn a micro-benchmark into a micro-benchmark. If you have code like this, you simply run the code under a very tight loop, as tight as possible, multiple times. This will avoid the function call of this substrate here, and it will give you a much more reasonable measurement of what you are looking for. And just where we benchmark. I was going to say use benchmark forking, and this is what David Golden decided to use for his benchmarks in the same blog post. But the problem is that he came to benchmark forking for the win when he cut the difference from 30% to 6%. Right. Not exactly what we're looking for either. We want to know whether we're 1% faster or something like that. So currently for this, there are no solutions because I couldn't finish the thing that I wanted to write and to present you guys here because it turned out to be much more complicated. So all I wanted to say at this point is what I'm planning to do in the next month or so. I hope to to get to something that can actually reproduce numbers. I'm going to call it benchmark sane, maybe. It's just a work in progress name. But what I'm planning to do is have benchmark units that are entirely specified by a YAML-based template language, because YAML is very easy to write here documents for or in. And every single timing unit will be string eval, and not only it will be string eval, it will be sent to a different physical process. So you don't have forking, you don't have memory randomization, you don't have sorry, what the hell? You don't have any of these things. You have a process which is started fresh and is running just the unit that you want to time, and it exits. Nothing else happens. And hopefully, the only thing that will get in the way will be address randomization of libc, which can be turned off by an environment variable. And hopefully, this will let me arrive at identical numbers for micro-benchmarking. How far it will go, well, we'll see it next YAPC, I guess. And that's pretty much it. I have the presentation with all the links at this address. It's in my GitHub, and thank you very much. I don't have much time, but lunch is next, so if you have any questions for 2 minutes, I guess. Oh, there's not. Oh, well, there you go. So. Then I guess you can ask me questions in the hallway. Yes?
This was more an observation about the repeatable. You won't necessarily found this yet, but I discovered to my utter confusion that if you rebuild the executable, it can run with different timings reliably. This was down to having the same object files linked in a different order, and everything within those object files had been built with 64-byte alignment, so it was aligned properly on the L1 cache, and I still don't know why. So, whilst you may be able to name it for the same executable doing it, taking the discipline and rebuild, you might still not be repeatable, just there's so many stupid things happening.
Oh yeah, absolutely. But here the point is to fix the code that you have control over.
Yes,
so, this is just part of it, obviously.
Yes.
Yeah.
I'm just saying you may not get the same numbers for the same compiler option when you rebuild, but
right.
that, what you're trying to do looks like useful progress.
Right.
Please do it.
Thank you. Yes. It solves about 25% of it only. Yeah. It helps, but it's not like it's not even half of it. Well, thank you.